But if gravity were geometry, light would have no choice but to follow the curved paths laid out beneath it. The test came during a solar eclipse in 1919. As the moon briefly blocked the sun, stars near its edge became visible. Their apparent positions were measured carefully and compared to where they should have appeared if space were flat. They were shifted. The starlight had bent slightly as it passed near the sun, exactly as general relativity predicted. The effect was small but unmistakable. Geometry had left a visible signature on the sky. Since then, light bending has been observed repeatedly and with increasing precision. Entire galaxies act as lenses, warping and magnifying the light of objects behind them. Rings, arcs, and distorted shapes appear not because light misbehaves, but because space-time curves on cosmic scales. Astronomers now use this effect routinely. It allows them to map invisible mass, including dark matter, by observing how space-time bends light around it. What began as a theoretical prediction has become a practical tool. Time, too, revealed its flexibility. General relativity predicted that time should run at different rates depending on gravity. Clocks closer to massive objects should tick more slowly than clocks farther away. This was not a metaphor. It was a measurable difference. At first, the effect seemed too small to notice, but as clocks became more precise, the difference emerged clearly. Atomic clocks placed at different heights above Earth drift out of sync exactly as predicted. A clock on a mountain runs slightly faster than a clock at sea level. The difference is tiny, but real. Satellites orbiting Earth experience both weaker gravity and higher speeds. Both effects alter time. Their onboard clocks tick at rates different from those on the ground. Without correction, navigation systems would quickly become unreliable. NASA accounts for these differences continuously. Positioning systems depend on timing accuracy, measured in billionths of a second. Ignoring space-time effects would cause errors to grow by kilometers each day. What once sounded abstract now quietly keeps everyday technology working. Motion adds another layer of confirmation. Clocks in motion tick more slowly than clocks at rest. This has been tested with aircraft carrying atomic clocks, with particles racing through accelerators, and with satellites circling Earth. Every experiment agrees. Time adjusts with motion. In particle laboratories, unstable particles moving near the speed of light survive longer than expected when measured from the laboratory frame. Their internal processes slow down relative to observers at rest. This is not interpretation. It is counted in detectors and recorded in data. Facilities like CERN rely on these effects as part of routine operation. Predictions would fail without them. Entire experimental programs depend on space-time behaving exactly as described. Even Earth itself confirms the picture. The planet's rotation and gravitational field influence how time passes across its surface. Extremely precise clocks can detect differences between continents, elevations, and even subtle changes caused by tides. Time is not uniform across Earth. It varies with position and motion, just as space-time predicts. These confirmations share a quiet quality. There is no single dramatic moment where space-time announces itself. Instead, it appears wherever measurement becomes careful enough. In light paths, in clock rates, in particle lifetimes, in satellite systems. The consistency is the key. Each effect could be dismissed individually as an anomaly or technical detail. Taken together, they form a pattern too coherent to ignore. Space and time behave as parts of a single structure. They stretch, bend, and adjust together under mass and motion. This is not interpretation layered on top of data. It is the simplest description that fits all observations at once. Importantly, none of this requires belief. It requires calibration. Engineers, astronomers, and physicists do not debate whether space-time exists when designing systems. They use it. The theory earns its place by working, repeatedly, quietly, reliably. The universe seems remarkably cooperative in this regard. It does not hide space-time's influence behind rare phenomena. It writes it everywhere, from the bending of distant galaxies to the timing signals guiding phones and vehicles on Earth. What changes with familiarity is not the evidence, but the sense of strangeness. At first, curved space-time sounds exotic. Over time, it becomes routine. Light bends, clocks drift, orbits precess, predictions match measurements. The unusual becomes ordinary. This is often how reality reveals itself, not with spectacle, but with consistency. Space-time is not an abstract idea floating above observation. It is a framework tested against nature and found to fit, again and again, across scales vast and small. The sky itself carries the record, in bent starlight, in delayed signals, in warped images of galaxies billions of light-years away. These are not artistic distortions, they are measurements of structure. When the universe is read carefully, it does not describe space and time as separate stages. It presents them as a unified geometry, one that shapes motion, guides light, and governs the passage of events. What once seemed like an intellectual convenience reveals itself as a physical reality. Space-time is not a metaphor, it is written into the sky. From the inside, space-time does not feel dramatic. There is no sensation of bending or stretching beneath the feet, no awareness of geometry guiding each step. Life unfolds at a human pace, where mornings arrive, bodies tire, and rest restores what motion spends. Everything feels still enough to ignore the deeper structure entirely. And yet, every moment of living is a journey through space-time. Aging is the most familiar example. Cells divide, proteins fold, memories accumulate. None of this happens outside time. Each biological process traces a path forward through duration. From a space-time perspective, aging is not something that happens to time. It is something bodies do within it, a steady progression along a personal route through the universe. Resting, too, is motion of a different kind. Lying still does not pause time or halt movement. The body continues to age, breathe, and repair. The planet rotates. Earth orbits the sun. The solar system drifts through the galaxy. Even at rest, nothing stops. Stillness, it turns out, is a local illusion. From everyday experience, standing still feels like the absence of motion. Feet are planted. Surroundings appear fixed. But physics paints a busier picture. Earth rotates once roughly every 24 hours. At the equator, that motion carries everything eastward at more than 1,000 kilometers per hour. Earth also orbits the Sun at about 100,000 kilometers per hour. The Sun itself moves through the Milky Way even faster. All of this happens quietly, without sensation. The reason is simple. Motion only feels like motion when it changes. Smooth, steady movement fades into the background. This is why riding in an airplane at cruising altitude feels calm, while turbulence demands attention. The body notices acceleration, not constant speed. Space-time treats all motion the same way. There is no preferred state of rest. Standing still on Earth is simply moving along with Earth's space-time path. From another perspective, it is a complicated curve through space and time combined. Walking adds another layer. A person walking across a room changes position in space while continuing to move forward in time. From a space-time point of view, the path tilts slightly. More motion through space means slightly less motion through time, though the effect is far too small to notice at human speeds. This trade-off becomes important only when speeds approach the limits allowed by nature. At everyday velocities, time behaves as expected. A walk does not noticeably slow aging. The universe is forgiving at human scales, but the principle remains: motion through space and motion through time are linked. Everyone is always moving through space-time at a combined pace. How that motion is divided depends on speed, gravity, and circumstance. Even standing quietly involves constant progression through time. The path does not pause. It simply follows the straightest route allowed by the surrounding space-time. This perspective reframes familiar experiences gently. Sleep, for example, feels like a gap. Hours pass unnoticed. Conscious awareness switches off, then resumes. From the outside, however, nothing stops. The sleeper continues along their space-time path. Processes continue. Clocks advance. The difference lies only in perception. Waiting works the same way. Time feels slow when attention is fixed on it. It feels fast when attention is elsewhere. Physics does not adjust for impatience or boredom. The structure remains the same, only experience changes. This contrast highlights an important distinction. Human time is psychological. Physical time is structural. Psychological time stretches and compresses based on emotion, attention, and memory. Physical time orders events regardless of how they are felt. Space-time concerns itself with the latter, not the former. The separation explains why time can feel inconsistent without being inconsistent. Experiments with precise clocks show no sympathy for human experience. Atomic clocks tick steadily, whether they are watched or ignored. They respond to motion and gravity, not mood. Their behavior matches space-time predictions exactly. NASA relies on this reliability constantly. Space missions depend on precise timing to navigate vast distances. Signals traveling between Earth and spacecraft must be accounted for carefully. Delays caused by distance and motion are not inconveniences. They are features of space-time that engineers work with daily. Even the act of measuring time reveals constant motion. A clock does not measure time flowing past it. It counts repetitive processes occurring within it. Vibrations of atoms, oscillations of electromagnetic fields. Each tick marks an event, a location in space-time. The sequence of ticks traces a paille. From this view, a lifetime is not something time does to a person. It is the path a person traces through space-time from birth onward. This idea may sound abstract, but it quietly simplifies many things. There is no need to imagine time pushing people forward or dragging them along. There is no universal conveyor belt carrying everything toward the future. There are only paths, each one shaped by circumstances, motion, and gravity. Some paths are steeper through time and slower through space. Others tilt differently, but all are valid. All exist within the same structure. Even the idea of being present changes subtly. The present moment feels sharp and immediate, but physically it is simply the current location along a personal space-time path. There is no cosmic spotlight marking now across the universe. Each observer carries their own present with them, defined locally. This does not make reality fragmented. It makes it intimate. Space-time does not demand a shared stillness. It accommodates constant motion effortlessly. It allows planets to orbit, cells to divide, clocks to tick, and people to pause for breath without ever stopping the deeper progression. Underneath quiet moments, motion continues, not hurried, not forced, just steady and precise. Every heartbeat, every breath, every step taken or not taken is part of a continuous journey. Not through space alone, not through time alone, but through both together. Living inside space-time means never truly standing still, and yet it also means that stillness can feel peaceful, because motion does not need to announce itself to be real. It simply carries on, calmly, beneath everything. Once space and time are understood as deeply connected, a curious question begins to surface. If they form a single structure, can one exist without the other? Could there be space with no time passing through it? A universe frozen, extended, but utterly still. At first glance, the idea seems simple. Space feels tangible. It can be pictured as a vast expanse, even if nothing happens within it. Time, by contrast, feels like the ingredient that brings change. Remove time and perhaps space could remain, like an empty stage after the play has ended. Physics approaches this idea more cautiously. In the physical description of the universe, space is not defined independently of events. It is defined by relationships. Distances matter only because something can be here rather than there. Positions matter because something occupies them, even if that something is only a field or a particle. Without events, space becomes strangely difficult to specify. This becomes clear when physicists attempt to describe a frozen universe. Imagine a cosmos where nothing changes. No motion, no interaction, no processes unfolding. Every object, if objects can still be said to exist, remains exactly as it is. From the inside, nothing would be observable. No clocks could tick because ticking requires change. No measurements could be made because measurement is itself an event. Without time, observation collapses. This does not mean such a universe is logically impossible. It means it resists physical description. In physics, space is not an abstract grid floating independently of activity. It is defined through interactions and relationships that unfold over time. Remove time, and the very tools used to describe space lose their meaning. This is why frozen universes tend to exist more comfortably in mathematics than in physics. Mathematically, it is possible to write down static structures, geometries that do not evolve, shapes that simply are. These descriptions are internally consistent. They do not contradict themselves. But physics demands more than consistency. It demands connection to observation. A universe with space but no time would offer no observations. No signals could travel. No light could propagate. No distances could be compared. Because comparison requires a sequence of events. Even the act of defining a location requires some process that distinguishes it. Physics resists descriptions that cannot, even in principle, be tested. This resistance shows up clearly in cosmology. When scientists describe the large-scale structure of the universe, they do not speak of space alone. They describe space-time evolving. Expansion, curvature, and structure formation are all changes. They rely on time as much as on distance. Attempts to remove time entirely tend to turn dynamic questions into static puzzles that no longer resemble the universe we observe. Even so, physicists have explored the idea carefully. Some approaches ask whether time could emerge from a more fundamental description, while space exists at a deeper level. Others reverse the question, asking whether space might emerge from more basic relationships, with time playing a different role. In these discussions, time often proves harder to eliminate than expected. Space without time struggles to accommodate causality. Cause and effect rely on order, one event leading to another. Without time, there is no before or after. Physics relies heavily on this ordering. Laws describe how systems evolve. Predictions depend on sequences. A static universe allows no evolution. Laws lose their purpose. Prediction becomes meaningless because nothing can change. This does not make the idea useless. It makes it limited. Frozen descriptions can be helpful as approximations. Physicists sometimes describe systems as static to simplify calculations. A star may be treated as unchanging over short intervals. Space near Earth may be treated as fixed for everyday engineering. These approximations work because time is still present, just temporarily ignored. Remove time completely, and the approximation breaks. There's also the question of information. Information is not a static thing. It is encoded, transmitted, and transformed. All of these processes require time. A universe with space but no time would be unable to store or communicate information. Without information, distinctions fade. Structure becomes meaningless. This is one reason physics tends to treat space-time as the fundamental arena, not space alone. Even in theories that explore exotic possibilities, time remains stubbornly present. It may behave strangely. It may emerge from deeper principles. It may even break down under extreme conditions, but it rarely disappears entirely. That said, physics does not close the door completely. At very small scales, near the limits of current understanding, some theories suggest that the familiar notion of time may dissolve. In these regimes, space and time may both give way to something more abstract. Whether that something resembles space without time is still unclear. What physics resists most strongly is not the absence of time, but the absence of consistency. Any proposal must still allow for cause and effect, for measurable relationships, for a way to connect theory with observation. Space alone struggles to meet these demands. This is why most physical descriptions return, again and again, to events rather than structures. Something happens. That happening defines both where and when. Remove either aspect, and the description becomes incomplete. The idea of space existing without time remains intriguing precisely because it highlights how much of reality depends on change. It invites imagination without granting certainty. Perhaps space could exist as a static geometry, timeless and unchanging. Perhaps such a structure could exist without observers, without processes, without history. Or perhaps space, like distance and position, only gains meaning through temporal relationships. Physics for now leans toward the latter, but it does so gently. There is no final declaration here, no definitive ruling, only a careful boundary drawn between what can be described, what can be measured, and what remains speculative. The question remains open, not because it lacks importance, but because it reaches beyond current evidence. Can space exist without time? Physics does not say no. It simply says that if it can, it would be very different from anything that has ever been observed, and that uncertainty held calmly leaves room for curiosity to continue its quiet work. If space without time feels strange, the mirror question feels even stranger. Can time exist without space? Can moments pass if there is nowhere for them to unfold? Can duration survive without distance, structure, or location? At first glance, time alone feels easier to imagine. After all, time is often treated as something abstract. It is counted, remembered, anticipated. It seems less tied to physical form than space. One might picture time flowing even if nothing occupies it, like an empty schedule waiting to be filled. Physics approaches this idea with careful hesitation. In physical descriptions, time is not a freestanding substance. It does not exist independently as a ticking background. It gains meaning through change, and change requires something to change. Without space, there are no positions to shift between, no configurations to rearrange, no relationships to evolve. Time without space begins to lose its anchor. This becomes clearer when considering what time actually measures. A clock does not detect time itself. It tracks repeated physical processes. Vibrations, oscillations, transitions between states. Each tick marks an event. Remove space, and those processes lose their setting. Even the simplest clock requires structure. Something must exist in one state, then another. Those states must be distinguishable. Distinction requires separation. Separation requires space, even if that space is microscopic or abstract. Without space, sequence collapses. Physics relies heavily on order. One event follows another. Cause precedes effect. Signals propagate. All of this assumes a framework where events can be located relative to one another. Time provides order, but space provides context. Remove context and order becomes meaningless. This is why time alone struggles to stand as a physical concept. It can be labeled, but not operationalized. It can be imagined, but not measured. Cosmology brings this issue into sharper focus. When scientists describe the history of the universe, they do not speak of time unfolding in isolation. They describe space-time evolving together. Expansion is not something that happens in time to space. It is something space-time does as a whole. Measurements of the universe's early stages rely on this partnership. Observations of distant galaxies reveal not only how far away they are, but how far back in time they appear. Distance and age arrive together in the same signal. NASA routinely interprets these observations through space-time models. When telescopes detect ancient light, they are not simply looking far away. They are looking deep into cosmic history. Space and time are inseparable in the data. This inseparability becomes especially important near the beginning. As scientists trace the universe backward, space contracts, distances shrink, densities rise, temperatures increase. Time does not tick alone. It is bound to the changing structure of space itself. Approaching the earliest moments, familiar descriptions begin to strain. The idea of time flowing through a fixed background stops making sense because there is no fixed background. Space itself is evolving rapidly. The framework that gives time meaning is changing. In these extreme conditions, the notion of time existing independently becomes hard to support. Some theoretical approaches explore whether time might emerge from deeper relationships, perhaps arising from quantum processes or informational structures. In these views, time is not fundamental, but a derived concept that appears only when systems interact in certain ways. What these approaches share is an acknowledgement that time requires structure. Whether that structure is spatial, relational, or informational, time does not stand alone. Even attempts to define time purely mathematically tend to rely on parameters that represent change within a system. Without a system, the parameter has nothing to describe. This does not mean time is unreal. It means it is contextual. Human experience often blurs this distinction. Time feels personal. It speeds up during joy, slows during boredom. These variations are psychological, not physical. They reflect how attention and memory work, not how space-time behaves. Physics remains indifferent to this experience. It treats time as an ordering tool, not a sensation. That ordering only becomes meaningful when events can be distinguished, compared, and related. Without space, events cannot be separated. Without separation, sequence collapses. Without sequence, time loses its role. There is also the issue of causality. Cause and effect require not just order, but influence. Something must affect something else. Influence travels. It propagates. Even at the speed of light, it requires a medium of relationships. That medium is space-time. A universe with time but no space would have no way for causes to produce effects. Everything would happen everywhere and nowhere at once. Physics does not support such a description. That said, physics does not close the discussion entirely. At the deepest levels of current theory, near the limits of quantum gravity, the familiar concepts of space and time may dissolve together. Some models suggest that neither space nor time is fundamental, but that both emerge from more basic ingredients. In these models, asking whether time can exist without space may be like asking whether temperature can exist without particles. The question assumes a separation that may not apply. Still, within all tested physical descriptions, time without space remains elusive. Whenever time appears, space or structure appears with it. Whenever space disappears, time becomes undefined. The two rise and fall together, at least within the universe that has been observed. This parallel with the earlier question is not accidental. Space without time struggles to support change. Time without space struggles to support meaning. Each lacks what the other provides. Rather than opposing concepts, they appear to be mutual supports. Remove one, and the other becomes unstable. This does not diminish time, it grounds it. Time is not a lonely river flowing through nothingness. It is a dimension woven into structure. It orders events, but those events must exist somewhere. As cosmology continues to explore the earliest moments of the universe, these questions grow sharper. What existed before familiar spacetime emerged? Whether such a before even makes sense? Whether time itself had a beginning? Those questions are approached carefully without rushing to conclusions. For now, what can be said is modest and precise. Time gains meaning through structure. It orders change, but it does not create it alone. Without space or something playing a similar role, time loses its footing. The mirror question remains open, but it reflects the same pattern. Just as space alone struggles to exist meaningfully without time, time alone may not stand without space. And in that shared dependence, the unity of space-time quietly asserts itself once more. When the universe is followed backward with care, something unexpected happens. The familiar stage on which everything unfolds begins to shrink along with the story itself. Distances shorten, temperatures rise, structures simplify. Eventually, even space-time, the framework that holds space and time together, starts to lose its familiar meaning. This idea did not appear suddenly. It emerged slowly, built from many independent observations that quietly pointed in the same direction. Galaxies are moving away from one another. The farther they are, the faster they recede. This pattern, measured carefully over decades, suggests that space itself is expanding. Not objects moving through a fixed background, but the background itself stretching. If space is expanding now, then earlier it must have been smaller. Tracing that expansion backward leads to a universe that was denser, hotter, and more tightly packed. Matter and energy were closer together. Light was trapped in a fog of charged particles. Structures like stars and galaxies had not yet formed. This is not speculation. It is supported by several independent lines of evidence. One of the clearest is the faint background glow that fills the universe. Discovered accidentally in the mid-20th century, this radiation is remarkably uniform and arrives from all directions. It carries the signature of a universe that was once hot, dense, and nearly featureless. NASA has studied this background radiation in exquisite detail using space-based observatories. Tiny variations in its temperature reveal how early structure formed. These measurements match predictions made by models in which space-time itself was evolving from a simpler beginning. Another line of evidence comes from the abundance of light elements. The proportions of hydrogen, helium, and lithium observed today align precisely with calculations of nuclear processes that would have occurred when the universe was young and extremely hot. These calculations depend on both time and space evolving together in the early cosmos. Taken together, the evidence suggests that space-time did not always look the way it does now. As scientists push these models further back, they reach a limit, a point where densities become so high and distances so small that current physical descriptions break down. Equations stop producing sensible answers. Familiar concepts lose their footing. This limit is often described as the beginning of space-time. That phrase can sound dramatic, but it is better understood as a boundary of knowledge rather than a violent event. It marks the point beyond which existing theories no longer apply. Not because something exploded, but because the framework itself was coming into being. At this boundary, asking what happened before becomes problematic. Before implies time. where implies space. If space-time itself is emerging, then those questions may not be well defined. It is not that there is an answer being withheld, it is that the language no longer fits. This is one of the most difficult ideas to absorb because it conflicts with how thinking usually works. Causes precede effects. Moments lead to other moments. Stories have beginnings that occur in time and place. Here, the beginning is of time and place themselves. This does not mean that nothing existed. It means that whatever existed did not exist within space-time as currently understood. The universe may have been governed by deeper principles, ones not yet fully described. Physicists approach this region cautiously. Some theories suggest that space-time emerged smoothly from an earlier phase. Others propose that familiar concepts dissolve into something more abstract, where notions like distance and duration no longer apply. These ideas are actively explored, but none are yet confirmed. What is consistent across approaches is the recognition of a boundary. Up to a certain point, space-time behaves predictably. Expansion can be measured, curvature can be calculated, time orders events. Beyond that point, the tools stop working. The universe does not offer clear answers, only silence where questions lose meaning. Importantly, this boundary is not a wall in space. It is not a location that could be reached by travelling far enough. It is a limit in time itself, a limit to how far the story can be extended backward using current understanding. This is why cosmologists speak carefully. They do not describe the beginning as a moment in time, but as the earliest moment time itself can be meaningfully defined. The distinction matters. The calmness of this picture is often overlooked. There is no need for fire or shock or sudden motion. The beginning of space-time can be described as a gradual unfolding of structure, relationships becoming defined, distances acquiring meaning, durations beginning to order events. From that perspective, the early universe was not chaotic. It was simple. As space-time expanded and cooled, complexity emerged naturally. Particles formed, forces differentiated, matter clumped, stars ignited, galaxies assembled. Time did not drive this process. It ordered it. Space did not contain it. It enabled it. Even now, space-time continues to evolve. Expansion has not stopped. The universe is still changing its scale, still shaping the context in which events occur. The beginning was not a finished act. It was the start of an ongoing structure. This view also reframes what beginnings mean more generally. In everyday experience, a beginning happens within an existing setting. A door opens, a clock starts, a journey begins from somewhere. The beginning of space-time does not fit this pattern. It is not an event within the universe. It is the emergence of the framework that allows events to exist at all. That subtle difference matters. It suggests that the universe did not begin in space and time. Space and time began with the universe. This idea is not presented as a final answer. It is a conclusion drawn carefully from evidence, open to revision as understanding deepens. Physics remains humble at these limits. But even with that humility, the implication is clear. There was a stage where there was no stage, a period where distance and duration had no meaning, a boundary beyond which the words before and after no longer apply. Once that idea settles, quietly and without drama, it leaves a simple realization behind. Space-time, for all its vastness and familiarity, has a history, and before that history began there was no space, there was no time, there was only the silence where structure itself had yet to appear. As space-time settled into its role as the quiet structure beneath gravity and motion, physics appeared, for a time, remarkably complete. Relativity described the large-scale universe with precision. Geometry explained gravity. Observation confirmed prediction again and again. Then physics looked closer. At the smallest scales ever measured, nature behaved very differently. Particles did not follow smooth paths. Outcomes became probabilistic. Events resisted precise prediction. The tidy geometry of spacetime began to look less certain when examined up close. This was not a failure of measurement. It was the domain of quantum physics. Quantum theory excels where relativity does not. It describes atoms, particles, and interactions with extraordinary accuracy. It powers modern electronics, lasers, medical imaging, and the devices that quietly fill everyday life. Its predictions are among the most precise ever tested. And yet, when quantum physics and relativity are placed side by side, tension appears. Relativity treats spacetime as smooth and continuous. Geometry bends gently under mass and energy. Motion follows well-defined paths. Everything fits together cleanly. Quantum physics, by contrast, thrives on discreteness and uncertainty. Quantities come in smallest possible units. Outcomes are described by probabilities rather than certainties. Smoothness gives way to granularity. When physicists try to apply both descriptions at once, cracks appear. At the smallest scales imaginable, spacetime itself begins to misbehave. Calculations predict wild fluctuations. Geometry loses stability. The idea of a smooth structure breaks down. The equations stop cooperating. This does not mean either theory is wrong. Each works extremely well within its own domain. The problem arises only when both are required at the same time, such as near the earliest moments of the universe or deep inside black holes. In those extreme conditions, space-time may not behave as a smooth background at all. This possibility has led physicists to a quiet but profound suspicion. Space-time itself may not be fundamental. Just as temperature emerges from the collective motion of particles, space-time may emerge from deeper ingredients. Ingredients that do not look like space or time individually, but give rise to them when viewed at larger scales. This idea is not new, but it has gained increasing attention as experiments probe deeper into nature's foundations. Facilities like CERN explore particle interactions at energies high enough to reveal subtle patterns. While these experiments do not directly observe spacetime breaking down, they test the limits of existing descriptions. They help identify where familiar concepts begin to strain. At the same time, theoretical work has explored many possibilities. Some approaches suggest that spacetime is built from tiny discrete elements, linked together like a vast network. Others propose that spacetime emerges from relationships between quantum states, with geometry appearing only when those relationships become sufficiently organized. In some models, distance is not fundamental. It is derived. Events appear close or far apart because of how strongly they're connected, not because of any underlying spatial grid. In others, time itself emerges from change, rather than existing as a background parameter. Ordering appears only when systems interact and information flows. These ideas can sound unsettling, but they share a calming feature. They do not discard space-time, they explain it. Just as solidity emerges from atoms that are mostly empty space, the smooth space-time described by relativity may emerge from a deeper, less intuitive layer, one that becomes invisible when viewed from a human scale. Importantly, none of these ideas are confirmed yet. They are careful proposals guided by mathematics and consistency, rather than direct observation. Physics remains patient. It does not rush to declare victory. What is striking, however, is the convergence. Independent approaches developed by different groups using different assumptions keep circling the same conclusion. Spacetime behaves beautifully at large scales, but may dissolve into something else at very small ones. This mirrors earlier discoveries. Solidity once seemed fundamental until atoms were discovered. Continuity once seemed obvious until quantum theory revealed discreteness. Spacetime now occupies a similar position, indispensable, accurate, and perhaps emergent. Even the language of modern physics reflects this caution. Researchers increasingly speak of spacetime as effective, reliable where tested, approximate rather than ultimate. This does not weaken relativity, it strengthens it by placing it in context. Relativity describes how spacetime behaves once it exists. Quantum approaches may describe how spacetime comes to exist at all. The tension between the two is not a contradiction to be erased, but a clue. It suggests that the universe may be layered, that familiar structures arise from deeper rules, that geometry itself might be a large-scale expression of something quieter underneath. This also reframes earlier questions. If spacetime had a beginning, perhaps that beginning involved a transition from a spaceless, timeless description to the one now experienced. If spacetime bends and stretches, perhaps it does so because it is not fundamental but responsive. In this light, the idea that spacetime might emerge from something deeper feels less radical and more natural. Physics has encountered this pattern before. Again and again, what appears basic turns out to be composed. What seems continuous turns out to be built from discrete steps. What feels absolute turns out to be contextual. Spacetime may be the next chapter in that story. For now, the evidence remains indirect. Experiments continue. Theories are refined. Observations push closer to the limits where new behavior might appear. What can be said calmly and carefully is this: spacetime works. It describes reality with remarkable accuracy across enormous ranges of scale. But it may not be the final layer. Beneath the geometry that bends light and shapes gravity, there may lie something more abstract, something relational, something that gives rise to distance and duration rather than requiring them. If so, spacetime would not be the foundation of reality. It would be one of its most beautiful consequences. After following spacetime through motion, gravity, beginnings, and quantum questions, a quieter issue remains. What exactly is spacetime? Is it a real thing in its own right, woven into the universe like matter and energy? Or is it a powerful description, a way of organizing relationships that feels solid only because it works so well? Physics does not rush to answer this. In everyday life, reality feels straightforward. Tables are real, clocks are real, distances feel tangible, time feels persistent. Spacetime, by contrast, is never encountered directly. It is inferred, measured through effects, reconstructed from patterns. That difference matters. Some physicists take spacetime to be fundamental. In this view, spacetime exists independently, much like a landscape. Objects move within it. Fields spread across it. Curvature shapes motion. Matter and energy interact with it, but do not create it from nothing. Spacetime is part of the universe's basic inventory. This perspective fits comfortably with general relativity. The equations treat spacetime as something that can bend, stretch, and respond. Geometry plays an active role. Gravity is not added on, it is built in. For many purposes, this view works beautifully. Observations support it. Light bends where spacetime curves. Clocks tick differently where geometry changes. Predictions match measurements across enormous ranges of scale. From this angle, spacetime looks as real as anything else physics deals with. Other physicists take a more cautious stance. They note that many things once thought fundamental turned out to be descriptive. Temperature feels basic, yet it emerges from the motion of particles. Pressure feels real, yet it is a collective effect. Even solidity dissolves under closer inspection. From this perspective, spacetime might be similar. It may not be an ingredient of reality, but a large-scale pattern that arises when deeper rules interact in certain ways. Geometry could be a summary, not a cause. Spacetime might be how relationships appear when viewed from far enough away. This view gains traction when quantum physics enters the picture. At very small scales, spacetime behaves awkwardly. Calculations suggest instability. Smooth geometry becomes difficult to maintain. Some descriptions stop making sense altogether. These hints suggest that spacetime may be an approximation, accurate but not ultimate. In this interpretation, spacetime is real in the way a wave is real. It exists, it can be measured, it has consequences. But it is not fundamental. It emerges from something more basic. There are also hybrid views. Some approaches treat spacetime as partly real and partly descriptive. Certain features may be fundamental, while others emerge. Time might arise differently from space. Geometry might be fundamental at large scales, but dissolve at small ones. Physics allows for these nuances. It does not insist on simple answers where complexity is warranted. Importantly, these perspectives do not fight with one another in practice. Engineers using satellite systems do not need to decide whether spacetime is fundamental. They need it to work. Astronomers mapping galaxies do not pause to ask whether spacetime is emergent. They use it because it describes observations reliably. NASA does not choose sides when navigating spacecraft. It applies the framework that matches reality at the scale of interest. That pragmatism is a feature, not a flaw. This highlights an often overlooked aspect of science. Reality does not demand a single metaphysical label to function. Multiple descriptions can coexist, each useful within its domain. A map can be accurate without being the territory. A rule can be reliable without being ultimate. Spacetime may occupy a similar role. When viewed from the scale of stars, planets, and people, spacetime behaves like a real structure. It bends, stretches, and guides motion. Treating it as real leads to correct predictions. When viewed from the scale of particles and quantum interactions, spacetime may look less solid. Relationships may come first. Geometry may follow. The same concept that feels fundamental at one scale may feel derived at another. This layered view of reality has precedent. Light behaves like a wave in some experiments, and like a particle in others. Neither description is wrong. Each reveals something true under specific conditions. Spacetime may be similar, sometimes a structure, sometimes a summary. The temptation is to ask which interpretation is correct. Physics resists that temptation. Instead, it asks which description works, where, and why. It values consistency over certainty. It prefers questions that can be refined to answers that must be defended. This approach allows uncertainty to be meaningful. Uncertainty here is not ignorance. It is a recognition of limits. A boundary where current evidence does not force a single conclusion. Within that boundary, multiple ideas can coexist, guiding research without closing doors. This openness has driven progress before. Atoms were once debated, waves and particles were once argued over. In time, deeper frameworks emerged that accommodated both perspectives without erasing them. Spacetime may be awaiting a similar synthesis. Until then, it remains both indispensable and mysterious, a structure that shapes reality, and a description that may arise from something deeper, a thing that feels real, and a concept that may not be final. Holding these possibilities together does not weaken understanding, it enriches it. Rather than demanding a verdict, physics allows space-time to remain slightly unresolved. Not vague, not confused, just open. That openness is productive. It invites new questions. It supports careful exploration. It keeps curiosity engaged without forcing premature conclusions. Whether space-time is the foundation of reality or a remarkably successful description, it continues to do its quiet work, guiding motion, ordering events, shaping the universe in ways that can be measured, tested, and trusted. And perhaps that is enough for now. Space-time does not need to declare what it ultimately is. It only needs to continue making sense of what happens, and it does. After tracing space-time from everyday motion to cosmic beginnings and quantum uncertainty, it becomes natural to ask why this question still matters. Why spend so much effort wondering whether space and time are the same thing? Why revisit an idea that seems settled enough to guide satellites, predict eclipses, and explain gravity? The answer is that space-time sits quietly at the center of some of the deepest questions physics can ask. Consider black holes. In these extreme regions, space-time is stretched and curved to its limits. Paths that once led outward now turn inward. Time itself behaves strangely. From a distance, objects appear to slow as they approach the edge. From nearby, everything continues as usual until familiar rules finally fail. Black holes are not just massive objects. They are laboratories where space-time is pushed to extremes. What happens there depends critically on whether space-time is fundamental or emergent. If space-time is the deepest layer of reality, then black holes represent its most dramatic expression. If space-time emerges from something deeper, then black holes may reveal cracks where that emergence breaks down. This question shapes how physicists think about what happens inside them, how information behaves, and whether anything meaningful can be said about their interiors at all. Cosmology faces a similar dependence. The history of the universe is written in space-time. Expansion, structure formation, and cosmic evolution all rely on how space and time behave together. Models of the early universe depend on whether space-time itself came into being smoothly, abruptly, or as a consequence of deeper rules. If space-time is fundamental, then its beginning marks a true boundary. If space-time emerges, then what appears to be the beginning may be more like a transition, where one description gives way to another. These distinctions are not philosophical decorations. They affect how models are built, what predictions are made, and which observations are sought. NASA designs missions based on assumptions about spacetime's reliability across enormous distances and timescales. Telescopes interpret ancient light using spacetime as their organizing framework. At the larger scale, spacetime determines how the universe expands. At the smallest, it determines whether known laws can be extended or must be replaced. Between those extremes lies everyday life. This is where the question quietly reconnects with experience. Every memory, every plan, every expectation rests on an assumption about time. Every movement, every location, every journey rests on an assumption about space. These assumptions feel so stable that they are rarely examined. Yet modern physics shows that they are not absolute. Time can stretch. Space can bend. Order can depend on perspective. What feels universal turns out to be contextual. This does not make reality fragile. It makes it richer. Understanding space-time reshapes how familiar experiences are interpreted. Aging becomes a path rather than a countdown. Movement becomes a negotiation between space and time rather than a simple change of position. Stillness becomes relative, not absolute. Even the idea of now becomes local. Each observer carries their own present, defined by motion and circumstance. This does not isolate individuals. It situates them precisely within the universe's structure. The question also matters because it guards against complacency. History shows that concepts once thought fundamental often turn out to be approximations. Air seemed continuous until molecules were discovered. Heat seemed basic until energy and motion explained it. Space-time now occupies a similar position. Powerful, accurate, possibly incomplete. By continuing to ask whether space-time is fundamental, physics keeps itself open to deeper understanding. This openness has practical consequences. New technologies often arise from questioning basic assumptions. Quantum mechanics once seemed abstract. Today, it underpins entire industries. Relativity once felt counterintuitive. Today, it guides navigation and communication. Future insights about space-time may reshape technology in ways not yet imagined, or they may simply deepen understanding, which has value of its own. There's also a quieter reason the question matters. Space-time shapes how reality is narrated. It determines how stories are told, how causes lead to effects, how beginnings and endings are framed. If space-time itself is not fundamental, then narratives about the universe may need to be told differently. The beginning of everything may not be a moment. The end may not be a place. Progress may not be a movement forward so much as a reorganization of relationships. These ideas do not erase meaning. They expand it. Importantly, none of this requires abandoning everyday intuition. Daily life works perfectly well within its own approximations. Clocks remain useful, distances remain navigable, cause and effect remain reliable. Physics does not ask for discomfort, it offers context. Space-time may be the language reality uses to speak at certain scales. At others, it may fall silent, giving way to a deeper grammar. Understanding where that transition occurs is one of the central tasks of modern science. And that brings the question full circle. Is space and time the same thing? After exploring motion, gravity, beginnings, and quantum hints, the question no longer sounds like a puzzle about labels. It becomes a question about structure, about whether separation is fundamental or convenient, about whether the universe prefers division or unity at its deepest level. The answer, for now, remains gently unresolved. Space and time behave as one in every test that can currently be performed. They bend together, they stretch together, they define events together. Whether they arise together from something deeper is still unknown. Perhaps the better question is not whether space and time are the same thing. Perhaps it is why the universe insists on treating them as inseparable, and in that softened form the question continues to matter. From the beginning, the question was never loud. It did not announce itself with urgency or demand a verdict. It simply lingered, quietly, beneath familiar experiences. Distance, duration, motion, waiting, aging, arriving, leaving. Space and time feel obvious because they never leave. Yet as the universe has been examined more carefully, that familiarity has softened. Space stretches, time slows, motion reshapes both. Gravity bends them together. Beginnings blur, certainty loosens. What once seemed like two separate ingredients begin to behave like one structure, or perhaps like two views of something deeper still. So the question returns, unchanged in wording but altered in meaning. Is space and time the same thing? Physics does not answer by pointing to an object or a substance. It answers with relationships, with events, with patterns that hold across motion and scale. Space and time appear less like containers and more like ways of describing how things are connected. Distance becomes a measure of separation between events. Duration becomes a measure of ordering. Neither stands alone. Each gains meaning through the other. From this perspective, space and time may not be things at all in the usual sense. They may be aspects of how reality arranges itself, ways the universe keeps track of change without needing a central clock or a fixed stage. This does not make them less real. Waves are real without being solid. Temperature is real without being tangible. Music is real without existing as an object. Space-time may belong to that same category. Something that emerges from relationships yet governs them in return. Whether space-time is fundamental or emergent remains open. Whether it dissolves into something deeper at smaller scales is still unknown. What is clear is that it works, quietly, reliably, everywhere it has been tested. Perhaps that is enough for now. Not every question needs to close. Some widen understanding simply by being held carefully. Space-time invites that kind of attention, It rewards patience rather than certainty. Space and time still feel separate in daily life. That feeling is useful. It keeps the world navigable. But beneath it lies a structure that is calmer, more unified, and more subtle than intuition suggests. Nothing needs to collapse into mystery here. There is no loss of clarity, only an expansion of perspective. The universe continues, events unfolding, paths traced, light travelling patiently across vast distances.